Logarithmic equations are equations where your variable is inside of the logarithm, and we have to use properties of logs to either condense or expand the logarithmic equation or expressions on each side, and then convert the logarithmic expression into exponential form, and that'll help us solve. All right, so here we go. In the past sections, we learned about logarithmic expressions and functions. Logarithmic functions are used to model processes that take a wide range of values as inputs and yields outputs restricted to a smaller scale. In this section, we will solve logarithmic equations and work on some applications of logarithmic models. We've seen logarithmic models previously when we were talking about, we did a couple problems with the Richter scale, like measuring how powerful an earthquake is, and it was another one. I can't think, but we'll do more applications later. All right, so solving logarithmic equations. A logarithmic equation with a logarithm on one side of the equation can be solved by rewriting the equation in exponential form. So if you look at example 1 here, I'm going to do some erasing. In example 1, all of these problems are some logarithm equals some number. So we only have logs on the left-hand side of the equation, and we have a number on the right-hand side. When our logarithmic equations are in this form, all we have to do is convert to exponential form and then solve the resulting exponential equation, or the resulting equation that we get. So for example, in problem A here, we have log of x is equal to 1/2. That's the common log, so our base is 10. We have to practice rewriting a logarithmic expression in exponential form. So we'll take our base, 10, whatever the log equals, that's our exponent, and then this would be equal to x. That's it. So 10 to the 1/2 power is equal to x. That's our solution here. X is equal to the square root of 10. Nothing else to do. So if we remember our rule for writing logarithmic expressions in exponential form, these aren't too bad to solve. If you need a refresher, we have log base b of x equals y is equivalent to the base to the y power equals x. All right, that's what we'll be solving here. For part B, log of x minus 5 equals 2. This would be 10 squared equals x minus 5. Now for this equation, we have a little bit more work to do to solve. 10 squared is 100. So 100 is equal to x minus 5. And then if we add 5 to both sides, 105 is equal to x. That's our solution for this one. All right, on to part C. In part C, we have a natural log, ln. So our base here is e. ln of x squared minus 5x plus 7 equals 0. This means that e to the 0 power is equal to x squared minus 5x plus 7. Okay, what is e to the 0 power? Anything to the 0 power is 1. So this would be 1 equals x squared minus 5x plus 7. And then this is a quadratic equation. We solve quadratic equations by putting them in standard form and then either factoring or using a quadratic formula. This one will become x squared minus 5x plus 6 equals 0. And this factors to x minus 6 times x plus 1. Okay, so our x values are x equals 6 and x equals -1. In cases like this, you do need to check to make sure both numbers actually work. And what do I mean by that? You're probably like, well, we solved it. Why wouldn't both numbers work? It is possible for you to get something called an extraneous solution. It's a solution to the quadratic equation, x squared minus 5x plus 6. But when we try to plug it back into the logarithmic equation, we get a problem. Please keep in mind that that's too big. The number that we're taking the logarithm of, so the term right here, this has to be greater than 0. We can't take the log of 0 or a negative number. So when we plug in 6, we get 6 squared minus 5 times 6 plus 7, is that a positive number? It is. That'll be 42 minus 30. So that'll be a positive number. And when we plug in negative 1 squared is 1, minus 5 times negative 1, that's plus 5 plus 7. Do we get a positive number? Yes. You do need to check that because all the time you won't get a positive number. Both of these do work though. Oops, so we get 2 solutions. Okay. And last one. Now for this last one, this one is not written in standard form. So our logarithmic expression is not isolated. So before we rewrite this in exponential form, we have to isolate the logarithm. So get the logs on one side, the constants on the other side. If we subtract 6, we have log base 2 of x plus 3 equals 8 minus 6, which is 2. Then writing this in exponential form gives us 2 squared equals x plus 3. And that's not bad to solve at all. 4 is equal to x plus 3, and subtracting 3 from both sides gives us 1 is equal to x. And if you check it, this would be true. If we plug in 1, that becomes log base 2 of 4. Log base 2 of 4 is just 2, and then 6 plus 2 is 8. So this does work out. All right. So again, if we have our equation written as the log is equal to some constant, we solve these by rewriting the logarithmic expression in exponential form and then solving the resulting equation. All right. So those problems were easily solvable by rewriting in exponential form, but sometimes you'll have problems where you have logarithms on both sides. Those require us to use this one-to-one property of logarithms, which tells us if we have a log base a of one number, m, is equal to log base a of something else, n. So the bases are the same, log of something equals log of something else. If the bases are the same, then the terms that we're taking the log of have to be equal also. An example of that would be like log base a, I don't know what a is, of 4 equals log base a of x minus 3. Both of these are log base a's, they're equal. If these things are equal, then 4 must be equal to x minus 3. Okay? It's kind of equivalent to when we say a to the x equals a to the y, means x is equal to y. The bases are the same, the exponents must be equal. Here, if the bases are the same for the log, the terms that we're taking the log of must be equal. So in example 2, log of x equals log of 49. All right, you might be thinking, first of all, 2 things are important. 1, it has to be log of something equals log of something else. That 2 in the front is giving us a problem. We're going to have to use properties of logs to fix that, okay? Also, you can only use this property if the logs on both sides have the same base. Both of these have common logs in problem A, so that's good. But with that 2 in the front, we can't use the one-to-one property yet. But remember, we have that power property of logarithms. We can take that 2 out front and write it as an exponent on the x. This would be log of x squared is equal to log of 49. All right, now this is written where we can use the one-to-one property. If log of x squared equals log of 49, then x squared is equal to 49. And then this is where you get an issue. So we would say x is then equal to, if you solve this equation, x would be equal to plus or minus the square root of 49, which means x equals 7 and x equals negative 7. But do both of these work? No. If we try to plug in negative 7, we get log of a negative number. This can't work because we can't take log of a negative number. So x equals 7 is our only solution. Again, please make sure you check when you end up solving a quadratic equation, make sure you check both solutions to see if you can actually plug them back into the original equation. Part B. 3 ln x equals ln of 27. So first we need to move that 3 up this becomes ln of x cubed equals ln of 27. And then since the ln's are the same, we have natural log on both sides. We can set x cubed equal to 27. And then to solve this, to get rid of a cubed, we use the cubed root. X cubed equals 27 means if we take the cubed root of both sides, the cubed root of x cubed equals the cubed root of 27. So x would be equal to 3. That's the cubed root of 27. And if we plug that in, it works. All right. Then part C, 2 log of x equals log of x, 2x minus 1. And we have to move that 2 up. So this would be log of x squared equals log of 2x minus 1. And then from here, we'll set x squared equal to 2x minus 1 and solve. So we get x squared minus 2x plus 1 equals 0. That's x minus 1 times x minus 1 equals 0. Is that right? Yeah, x minus 1 squared. Okay, so we just get one solution here. X is equal to 1. So now we have two cases that we know how to solve. If we have log base b of x equals y, we write it in exponential form. If we have log base b of x equals log base b of y, then we use the one-to-one property. All right, and let's keep pushing. So we already solved all of these. Next, we're going to have some practice problems where we use these properties. Guys, let's go through the solutions for these. So for problem A, 2 log of x equals log of 36. We can rewrite the left-hand side as log of x squared equals, and then the right-hand side, log of 36. Both of these are log base 10, so then we can say x squared is equal to 36. And then x would be equal to plus or minus the square root of 36, which is 6 and negative 6. However, the negative 6 doesn't actually work here because we can't take the log of negative 6 if we try to plug this back in. So x equals 6 is our only solution. For part B, ln of x minus 2 equals ln of 10. This one's already written in the form we need it in, so we can go straight to x minus 2 is equal to 10. Then x equals 12. That's it. And for part C, 2 log of x equals 4 log of 3. We can write the left-hand side as log of x squared and write the right-hand side as log of 3 to the 4th power. And then we'll get x squared equals 3 to the 4th power. So that's x squared is equal to 81. And x would be equal to plus or minus the square root of 81. So that's positive 9 and negative 9. But again, we can't take log of negative 9. So we can ignore that solution, and x equals 9 would be our only solution. All right. So far we've looked at logarithms where we have a logarithm equals a number. We said we put that in exponential form. And then we have a logarithm equals another logarithm. We said we can drop the logs and just set the terms equal to each other using a one-to-one property if the bases are the same. And then in the next section, we're going to look at problems where we have maybe the sum or difference of logs on each side of the equation. And we have to do a little simplifying using properties of logarithms before we use either of these properties. All right, so for example 3, if you look at the two problems we have here, log of x plus log of x plus 3 equals 1. And log of x plus 4 minus log of 5x plus 12 equals negative log of x. In one of these, A, we just have logarithms on one side of the equation and a number on the other side. In part B, we have logarithms on both sides of the equation. But neither of these are quite written in the forms that we've seen previously where we can either write an exponential form or use the one-to-one property. That's because on the left-hand side of these, we have more than one logarithm being added or subtracted. So we need to use the properties of logs that we have to condense logarithms to simplify the left-hand side of these equations. And then we can use the same techniques that we used in examples 1 and 2. All right, so for problem A, we have log of x plus log of x plus 3 equals 1. For log of x plus log of x plus 3, we can condense this into one single logarithm by multiplying the x and the x plus 3. So this is log of x times x plus 3. And then that's equal to 1 on the other side. X times x plus 3, this makes this log of x squared plus 3x equals 1. And then from here, we said if we have our logarithm equal to a number, we convert this to exponential form. This would be, log is base 10, so 10 to the first power equals x squared plus 3x. And then from here, we can simplify and solve. 10 equals x squared plus 3x. 0 equals x squared plus 3x minus 10. Then we get 0 equals x plus 5 times x minus 2. We get x is equal to -5 and x is equal to 2. Again, we have to check both of these answers. Looking at our original equation, if I try to plug in 2, I have log of 2, that's fine, and log of 2 plus 5, that's fine, okay? If I try to plug in -5, I get log of -5 and log of -2 plus a -5 plus 3, which is -2. I can't take the log of a negative number. -5 does not work as an answer, and only x equals 2 would be a solution. Part B. Here we have log of x plus 4 minus log of 5x plus 12 equals negative log x. So on the right-hand side, we can combine this into one log by dividing the terms. We'll have x plus 4 divided by 5x plus 12. So one logarithm, and then divide the two terms we're taking the log of. And this would be equal to, now on the left-hand side here, we have negative log of x. That's equivalent to log of x to the negative first power. Okay, let's rewrite just a little bit. So we have log of x plus 4 over 5x plus 12 equals, this is a little sideways, okay, equals log of 1 over x, because that's x to the negative first power. The logarithms are the same, so we can drop the logs and just solve the rational equation. X plus 4 over 5x plus 12 equals 1 over x. When we have an equation like this, we can cross multiply to solve. We get x times x plus 4 equals 5x plus 12. So x squared plus 4x equals 5x plus 12. And moving everything to one side gives us x squared minus x minus 12 equals 0. So we have to factor here. This would be x minus 4 times x plus 3 equals 0. So x equals 4 is one solution, and x equals -3 is the other solution. Now we need to check these. The 4 will work because that'll give us positive numbers here. For the -3, -3 plus 4 is 1, so it works for the first logarithm. But 5 times -3 plus 12, that's -3. So x equals -3 won't work as a solution. X equals 4 is our only solution. All right, so for these two, we had to use properties of log to simplify each side of the logarithm a little bit, and then either use the one-to-one property, like we did in part B, or rewrite an exponential form, like we did in part A. We want to try to solve these logarithms by simplifying, using the properties of logs on each side. And then for part A, you're going to use the one-to-one property. For B and C, notice there's just a number on the right-hand side of the equation. So you're going to use rewriting in exponential form. So let's go through the solutions for this one. For part A, ln of x plus 1 plus ln of x equals ln of 20. We have logs, natural logs on both sides. But before we can use the one-to-one property, we need to simplify the left-hand side. The left-hand side can be combined to get ln of x plus 1 times x, and then it's equal to ln of 20. So ln of x squared plus x equals ln of 20. And then we can drop the ln's and just set the x squared plus x equal to 20. And it gives us a quadratic equation to solve. X squared plus x minus 20 equals 0. So we get x plus 5 times x minus 4 equals 0. And our solutions are x equals -5 and x equals +4. If we try to plug -5 back in, we end up getting ln of a negative number. That doesn't work. So x equals 4 will be the only solution. All right, then on to part B. Log base 2 of x squared plus 6x plus 9 minus log base 2 of x plus 3 equals 3. We can condense this to log base 2 of x squared plus 6x plus 9 divided by x plus 3. And again, we're dividing here because the logs are being subtracted. In the previous one, we multiplied because the logs are being added. All right, and this is equal to just 3. So we can take this logarithmic equation and rewrite it in exponential form. Our base is 2. Our exponent would be 3. And this should be equal to x squared plus 6x plus 9 over x plus 2. All right, those are supposed to be 3's. X plus 3. Then we'll have 8 times x plus 3 equals x squared plus 6x plus 9. Then 8x plus 24 equals x squared plus 6x plus 9. Then 0 is equal to x squared minus 2x minus 15 equals 0. So 0 is equal to x minus 5 times x plus 2, which gives us x equals 5 and x equals -2 as solutions. The -2, that's a lie. All right, so only x equals 5 is a solution. All right, last one. Log of x squared minus 69 equals 2. Well, there's not much to do on this one. This is 10. We write it in exponential form. Base 10 to the second power equals x squared minus 69. That's 100 equals x squared minus 69. We add 69 to both sides. 169 equals x squared. And then if we take the square root, x is equal to plus or minus the square root of 169, which means x equals 13 and x equals -13. And both of those would work here because we're squaring them, so we'll get positive numbers. So these are our answers. All right. So we've seen pretty much all of the different types of logarithms that you would be expected to solve. The last thing we're going to do is talk about an application where logarithms are used. I mentioned previously that we had looked at, logs involving the Richter scale and measuring the magnitude of earthquakes. Another thing we can look at is logs that help us measure sounds, so decibel sounds. That's what the next function gives us. So the function that models the decibel level of sound, D, with sound intensity, I, is measured in watts per square inch, and it's given by a logarithmic function. D is equal to 10 log of I over 10 to the -12th power. And again, I is the intensity, and D would be the decibel level, okay? So number 4 goes through an example of how this can be used. We can just read through it and then we'll do one example of our own. It says, the decibel level of music coming through a pair of earphones is 100 decibel or dB. And what is that measured in again? Decibels per, or watts per inch. Oh no, the intensity is measured in watts per inch. The decibel is decibels, okay. So 100 decibels. What is the intensity of the sound? So in this case, we're given D, and we want to solve for I, the intensity. So if we plug in 100 for D, we get 100 equals 10 log of I over 10 to the negative 12th power. Okay, we can divide both sides by 10 to isolate the logarithm, and then we can write this in exponential form to solve. Log is base 10, so this would be 10 to the 10th power equals I over 10 to the negative 12th. 10 to the 10th power equals I over 10 to the negative 12th. And then to solve, we'll multiply both sides by 10 to the negative 12th. So 10 to the 10 times 10 to the negative 12th equals 10 to the negative second, and that's our value for I. So exercise 3, extended exposure to noise that measures 85 decibels can cause hearing loss. So if you wear your earbuds really, really high, that can mess up your hearing, and your hearing cannot be repaired. You have to get a hearing aid. So be aware of that. What is the intensity of sound with a loudness level of 85 decibels? Use the formula D equals 10 log of I over 10 to the negative 12th to solve. So this will be worked out the exact same way. We're told that D is equal to 85. So we'll have 85 is equal to 10 times the log of I over 10 to the negative 12. To solve this, we'll first divide both sides by 10 to get rid of that 10. 85 divided by 10 is 8.5. So we get 8.5 log of I over 10 to the negative 12. And then we can convert this to exponential form. This is a common log, so our base is 10. The logarithm is equal to 8.5, so our exponent is 8.5. And this is going to be equal to I over 10 to the negative 12th power. Then to solve this, we're going to multiply both sides by 10 to the negative 12. And using properties of exponents, we'll get 10 to the 8.5 minus 12 equals I. That would be 10 to the negative 3.5 equals I. And that's our answer. This would be 10 to the negative 3.5. We said the intensity was measured in watts per square inch, so watts per square inch. So the intensity is 10 to the negative 3.5 watts per square inch. All right, so this ends section 9.5, and it also ends all of the material that we're learning for the class. So yay!